Hello kidlets. So we left off talking about the sun and solar flares. We're just briefly going to touch on what constitutes a star, stellar formation, and fusion. So here, this is the Eagle Nebula. Here's the Horsehead Nebula. I'll show a video of that in class. These systems are both much larger than the solar system, and these are nebulas that are essentially conglomerates of gas and dust. So you have a ton of hydrogen that you can see is ionizing these areas of star formation behind it. So stellar nurseries, nebulas, are essentially where stars are born. So in order to actually have a star, you have to have something that causes that cloud to collapse and begin to rotate. So you have to have temperatures very, very high in order to actually begin fusion. And you have to have this collapse that leads to this quick formation of protostars. So it's about 100,000 years. Your range in stellar masses, it has to be 8% of the sun's mass, which is not what Jupiter is, which is why it is not our second sun. It has to be that size. That's a minimum mass size for stellar fusion to begin. And then most of our very, very large stars are around 100 solar masses. However, VY Canis Majoris is bigger than that. The T Tauri phase is important because this is what around sun-like stars gives us the formation of planets. The T Tauri phase is the planet-forming phase in which our sun, the solar nebula, ejected out enough material to form all of the planets, the inner and the outer, as well as the asteroid belt, which happened relatively quickly right after our star was born 5 billion years ago. So here's a little diagram of how that happens. Here we have our interstellar molecular cloud. Here's a protosolar cloud, which is beginning to condense. Here you have that flattening with the disk and the jet extending from the poles. Here you have a star with a disk. This would be our T Tauri phase. And here we have our star. So here we can see that animation again highlighted in 6 different steps. So here we have that dark cloud, which then collapses under the weight of its own gravity. So here we have that gravitational collapse that collapses inward. And it's important to point out that this whole cloud is not the size of the star. This is actually about 100,000 solar masses. So there could be many, many stars that are formed from one molecular cloud. So here we have our protostar forming at the center, and we have that disk and that envelope that is formed around it. Here we have the beginnings of our T Tauri phase, which is where we have planetary systems that begin to form from that disk. So here we have some pre-planetary debris. So here we can see some things forming around. So you can see that the bigger planets form outer, as you have the cooler ices that form away from the stars. They're ejected further. And then here we have a full planetary system. So fusion is essentially what makes a star and moves it beyond the stage of a molecular gas cloud. So we have 2 types of fusion. We have fusion that takes place within a sun-like star, and this is called the proton-to-proton chain. It is really hard to write with this pen, I'm sorry. And then we have the fusion that takes place inside massive stars, which is carbon fusion. So the fusion that takes place inside of our sun is hydrogen fusion. Which is what we're going to discuss now. And this is just the combining together of 2 or more lighter elements to produce heavier elements. But in a massive star, you can go on to fuse things beyond carbon. And in a massive star, we don't stop until that fusion reaches iron, which is the most dense element there is. And that's how we have supernovas. So we have hydrogen fusion, which is utilizing the proton-to-proton chain in a sun-like star. And then we have carbon fusion in a massive star. So here is a little diagram highlighting what's happening when you have fusion. So we begin with 4 hydrogen atoms. It actually begins before that with 2 protons. But here is just the gist of hydrogen burning. You have 4 hydrogen atoms that combine to get helium atoms. And then you have an expenditure of neutrinos. Now, one thing that is interesting to note is that when this process happens inside the sun, it can only take a few seconds for a neutrino to leave the sun. It can take over 1 million years for the fusion process to actually reach the surface of the star, to reach the photosphere. So the fundamental concept of fusion is that mass and energy are interchangeable, which is what Einstein proved. So when you have fusion, you're having these lower mass elements that are combining to form more massive elements. So in a sun-like star, the core reaches carbon. In a more massive star, you're able to fuse beyond carbon and reach iron. So in stellar cores, you have to have a temperature of at least 5 million Kelvin in order for those nuclei to combine. And that's called the Coulomb barrier. So the Coulomb barrier is this recombining, but remember that hydrogen atoms and protons have the same charge. So you have to have this really high heat in order to overcome that natural repulsion. And this really stumped physicists for many, many years because naturally positives do not attract. So the Coulomb barrier is the temperature that you have to have in order to overcome that natural repulsion. So this is what Einstein showed as well. So at 50 million degrees, which is about 5 million Kelvin, at the center of the star is where you get fusion. And here is his equation. So when you get 4 hydrogen together, you yield 4 helium and some excess energy. So here's another diagram of fusion. I apologize if you look close, there's a few things like some of these squares that shouldn't really be there, but when I uploaded to this program, they kind of weaved their way in. So this is a little more complicated than what I need you guys to know. Essentially, I just want you to know that the proton-proton chain is combining together protons to get your hydrogen, which forms helium and yields energy. So the breakdown of that, here you have your 2 protons. This little guy here, if we look down at the bottom, there's our neutrino. So the only places that neutrinos can be detected is underground. And the biggest and most effective neutrino observatory is a 2-kilometer deep well that's in Sudbury. I believe it's called the Sudbury Observatory. If you're interested in that, it's pretty fascinating because Sudbury is an actual impact site. So it's hit by a very large meteor many, many years ago. And they now have a well there because it is also a very profitable mine because of that impact site. So, side note. So there is the released neutrino that makes its way to Earth very, very quickly. So here we have the recombination of those 2 positrons to give us our hydrogen. Here we have our hydrogen that has fused together to give us our helium. So here you can see that we have the excess of gamma rays. So that's the energy that's being released because, remember, Einstein showed that for every particle of energy, you also have a unit of mass as well. So this results in a huge energy gain. The actual energy gained by the sun every time this fusion reaction happens is 25 million electron volts. So that means there's 25 million electrons required to overcome the energy of each volt, which is pretty darn big. And there has to be over 1,000 reactions in order for the sun to actually resist its own gravity in order to maintain equilibrium. So new stars are not quiet. These have huge explosions of gas. This is a young binary system showing here's a star here, here's a star here, and this is a binary system. So you can see both 2 stars together here, and here you have a huge ejection, so to where you can't even see that second star.